And he's going to tell us about collective motion, some models, and experiments.
Thank you. Let me first switch this on. Okay? Okay. It's not going to be easy to give a talk after this spectacular presentation by Ian, so there will be overlaps. But I'll try to go a little bit further and collect and build on what he said and show some other things. And as a physicist, to look for some general, as you say, universal features in this wide variety of phenomena that we just saw, and I'm going to show you. So I'll put collective motion. I'll talk about the motion aspect of collective behavior only in the context first, showing a few sort of funny examples for collective behavior in of a few kinds. So this is people are applauding. Look at this guy. He's behaving very strangely. Some other ones do the same in the audience. I could point that out. But he knows what he's doing, and soon he eventually succeeds. He's a kind of leader. And now it seems as if he made the other ones clap in unison according to his rhythm, which is, by the way, exactly or about exactly the half of our natural clapping frequency. This is a picture which shows people in a spa standing for hours, and they are trying to slowly drift away from each other and find the optimal solution, the triangular lattice, for this problem. So this is another collective behavior. This is something well known and discovered in this country, the rain, and we made a model of this also. There are people in the excitable state, and then they get down, and so this is a collective behavior acting in synchrony. This is not so much what I would like to talk about, but in fact, many of the synchronization phenomena can be mapped to collective motion, or rather collective motion into synchronization phenomena, because the phase sometimes of a rotator behaves like a direction. If you just take off the natural frequency, then the phase is like a direction. So I go to collective motion now, and then I zoom to a particular kind of collective motion, a particular pattern, and then I try to make a general statement. So this is something which other audiences not immediately recognize, that it is a bacteria. This is Proteus mirabilis invading, which so similar movies. They look like fish, but they are very different. These are the locusts. I think this might be from the paper published by Ian, just to demonstrate this is not a movie. He has the movies about this, and they march as we just learned. This is another picture of golden rays. It just looks beautiful, and this is from the same BBC movie for which Ian worked as an advisor. So this is all sorts of collective motion patterns. This is just something I very recently was trying the capabilities of my new notebook, not this one, and downloaded a high definition movie, and then it made it a lower resolution for this purpose, just to show you how beautiful these flocks can be. I mean, how sensitively these fish reflect on each other, even when it's not that terribly confusing motion pattern. Okay, I'll show you more examples just to raise the appetite, because then I'll become a little bit drier. So it's all about universality. So I'm trying to show paradoxical pictures. This you would assume are birds, but they are bats. This is very much like what Nia showed, this fantastic collective motion of starlings, European starlings. And this is also from the BBC movie here, just to show that you see group motion on the level of mammals, of course, like sheep. These are a little bit larger size. And this is something not very closely related, but I was fascinated by this shootage. I was watching Animal Planet and somehow. So I guess at least no one knows what this could be. These are tens of millions of bats followed by radar, and they are emerging from caves in Mexico. And this is the size scale is not very well seen, but it's many tens of miles, many tens of it. They cover a part of a whole state. And it's a collective motion behavior, because at some point they move together towards another flock of the same size, which is moth caterpillar. I don't know how to pronounce very well, but this is what these are examples then on collective motion. And this is part of my introductory regular talk, so I just very quickly show you that, of course, as we know, physicists also can produce these interesting motion patterns. As soon as you animate something, it starts to behave like an animal. And so here, and interestingly, I will come back to this system which was discussed during yesterday morning. You see something else. I would call this jamming. This is a nice simulation by them about this. This is just a still picture by Chate et al. About pneumatic, elongated particles producing some sort of coherence. So there are all sorts of patterns. And now I'm briefly talking about a single pattern. And it's, so there are various patterns, and I would like to say that all of them are universal in the sense that they occur from bacteria up to people, or I would say up to robots, if it's up to. And and now to make this point, I zoom on one pattern, kind of pattern, and it's the one that was also showed by Ian, and it's the circular motion of all sorts of animals in a closed area. This is fire ants, so we also have ants here, related to the first talk this morning. These are the locusts of the cuisine and collaborators, and these are our bacteria from 1996. So we will zoom now. This is a bacteria colony, and at that point we were more interested in the fractality. Fractals were the big thing. But then I noticed that this is something important, something interesting is going on here, and we sort of zoom on that spot, and in that spot, bacteria move in circles, just like fish or locusts. And in fact, if we go up, they are in several levels of bacteria, and they move very nicely and coherently. So we go up now from bacteria. We go to amoeba. We also saw this. Amoeba are aggregating, and in the middle they are producing a rotating mound. This is the middle part, and even this, which was new to me. This is all stolen from the internet. The slug itself rotates. The slug rotates as it moves, and then the stalk also rotates. So I guess I have some more examples to show you rotational motion. These are the same beds when they emerge. Before they start to move out, they are located above the cave, and they are rotating there. These are a well-known example of people showing the same pattern. And this is a long story on its own. But as we go above, from a helicopter view, it's almost like a bacteria colony. Now, there are also attempts to teach robots to move together. And even robots, when they are given the simple rule of follow each other. It's not so easy. Robots are less, it's really a tough thing to teach them. This is the lost sheep. This is very recent. This is 1 year old. This is the state of the art. And we plan to work on this. So now some also, this is our goal to classify these patterns, and as a physicist, just to assume that there is a deep analogy between equilibrium statistical mechanics phenomena and phenomena in systems which have also a tremendously large number of units, but these units are driven. So it sounds like a small difference, and indeed, these systems don't differ so much as it looks if you talk to a biologist showing the beautiful particular patterns of a given behavior. And of course, we see that also biologists like him, together with physicists, is moving in the direction of finding a unified picture for collective motion. This is a very short historical background that we understand these behaviors through modeling, of course. Everything in our mind is a model of reality. Anyway, so these are the simplest, the first attempt, which really grabbed attention, was by Craig Reynolds in 1987, and he already was obtaining very nice flocks. They were mostly flocks of starships, because he worked for the Hollywood and got a huge prize for his activity, because he was able to use those rules, the kind of rules Ian mentioned about repulsion and attraction, to produce extremely realistic starship flocks. Now, in 1995, we had the idea that these models could be made simpler, and also noise should be added, because otherwise you get a deterministic system of a couple of units which is oscillating and it's a chaotic in the sense that it has a specific randomness instead of the true randomness. But I will return to the randomness question. And there are many recent models as the topic is becoming more and more popular, and with all sorts of controversies and new results. And I would like, at this part, I usually mention that there are only a few pure theoretical results in this field. And I'm not going to present a theoretical result, rather a concept or a picture of these phenomena. But there is a network related to mean field calculation showing the nature of the phase transition in self-propelled particles models, and they show when it is first and when it is second order. This was also an amazing, a nice study, very recent, when they find, this is one of the most important perhaps papers supporting my point, that they find the kind of finite size scaling and the kind of hyperscaling relationship between exponents, critical exponents, for transitions in simple models, what you would see in an equilibrium statistical mechanics situation. And also, I very highly appreciated recently the organizers here were able to handle in an exact manner self-propelled rods, system of self-propelled rods, and also drew the attention of the specific nature of the boundary conditions. The boundary conditions in the world of self-propelled particles play a principally different role from that what the boundary conditions play in the world of equilibrium systems. This is on one hand almost trivial, this is your insight, but we still don't know the best ways to handle this. I will show you one example for that. So this is the simplest model we think, which was introduced in 1995 by us, which takes into account two things. One is that you try to align with your neighbors. Now, this alignment rule I could talk a lot about, because it seems to imply that I'm taking into account something arbitrary. I just assume it's an assumption of the model, but I could show you zillions of examples where the interaction, even if it doesn't look like an alignment rule, it is an effective alignment rule. I will get to that. So there is an alignment rule that what makes them move together, and there is noise. And the noise is also a long story. It can be, you can have a completely deterministic system. In a simulation, for example, of little perfect spheres. It is completely deterministic. But when you look at it, the way, we know that a system which consists of 100 equations, and all of those equations are deterministic, you very soon lose any coherence, it's chaotic. So there is a lot of noise in us. Or even if on the quantum mechanical level, things are, maybe even that level, it's not deterministic. So there's no two tennis games which are the same, even for a second. It's every collective phenomenon is just bound to have a lot of noise. And this had been ignored, so that was our point. So this model, so this is just an expression of the alignment. You get loss noise. So you put that into the computer. We did this long time ago. So this is so lively, in part because we were just making a video recording of the screen of the computer. There was no digitization, and the low tech gives a softer look. And here it's for a little bit larger density and for a smaller noise. And what I'm showing this for is to show you what happens what is the mechanism of the ordering in a system which moves. So this is the starting initial condition. This is the fish of Ian when they are just around, completely unaware or not caring about, maybe feeding, or birds feeding on the ground. And then you shoot a pistol and they start to move. So the birds go into air. I like the birds because they have to move. The fish can just stay in one place. The birds have to move, otherwise they would fall. So this is the 1/10 of a second what goes on in such a group. They immediately align with the neighbors, but then it still leads to vertices, but the vertices are unstable because of motion. It's easy to, they bump into each other. The vertices are stable in the XY model, in an equilibrium statistical physics model. These vertices they're not stable, they have zero energy, so they're marginally stable, if you wish. But here, they're truly unstable because there is an interaction range growing in time in the system as the units move to different parts of the system. So it goes from a local to a global interaction, and for global, we know there is ordering. That's the mean field. Okay, so the first set of more or less general remarks I would like to make. Some patterns of motion are universal, or they're the same. Statistically, they are the same. Simple models reproduce this behavior. Okay, let me show you. This is the simplest model with a hardcore repulsion for the particles. So they're trying to follow each other, but there's a hardcore repulsion so that they're not all collected at the edge of the circle on the boundary, and they immediately organize themselves. They're this is like locusts, and also in this quasi 1.5D simulation, you will see that due to the rule is simple, the system is complex. So due to that, there's a spontaneous turning of the direction, the directional switching, and then from some point they just start to move in the opposite direction. Okay, so there are sorts of waves also propagating, and okay, I already told about the noise term. It accounts for everything. It can be molecular level, it can be people, it can be even little hard balls. Many deterministic interactions add up to a completely randomly obtained effect. In most of the cases, the ordering is due to motion, as I showed, and even in this simple, the explanation for this, you start with random initial conditions, so the average momentum is about zero. The vectorial sum of the velocities times mass is zero. The kinetic energy is the same all the time because you drive each particle with the same velocity. So that's one thing. But the momentum changes during collisions. For an equilibrium collision, you would have that this would be the resulting momentum for an equilibrium collision. But with our interaction and our simple rules, they will move in a direction which is closer to what when they encounter each other, and they also have to move with this velocity, so the total momentum is much larger. So each collision increases momentum, and if this wins somehow, this is in a way bound to win. So you end up with a system which has a growing total momentum, and at the end, it just moves in a single direction. Okay, this is I touched on this extremely briefly, although it took a long time. You can do a careful analysis of the transition as a function of the noise parameter. It's a bit complicated, but it just wants to show that there is a shift for low temperatures, low noise level. You increase the noise level, and the order parameter goes to a different value. So there's a phase transition somewhere here, And because this is a one-hung density distribution for the order parameter that signals that this is a second order phase transition. There was some debate about this in the literature, which something is still open, but we thought we proved in this way that the transition is first order, second order. Sorry. Now, just a few visualizations of. Okay, this is a large visualization, and my computer is small and slow, and it doesn't even show up. Okay. So these are, each of these are look like birds. So this is the 3D simulation of that trivial model. But the particles are made of look like birds. And it is very realistic. Okay, so I'll show you some more. I'll show you this. I usually show other ones if there is more time. And here I would like to show that we add we add boundary, a column. So we say the particles are not allowed to move outside a vertical column. But they also like to be formed. And now this is the visualization. We are searching for a complex shape in the simulation with this visualization tool. And you see that we are not there. We cannot really simulate the complexity of starlings, but we are on the way. And this is already some sort of somewhat closer than the simplest model, without doing much more extra. It's just that the boundary conditions are there. Now, this is just for fun. We are sitting on the back of this bird. The camera is really attached to the back in the simulation. So we join the flock, and then there is another flock, a larger one, flocking, coming by like this, and so this flock joins it, and that's why this strange change in motion. Okay. So this is how far you can get with simple simulations, and if you can get far with simple simulations, then you have the idea that maybe there is something common in all of these phenomena. Here, I also connect to the talk by Ian, where he was talking about a not much understood situation when I always say particles, but birds or fish move in a very incoherent fashion, but they are together. So this is like this is terribly complex patterns, and we can produce that if we introduce a new term in the simplest model, which also counts for acceleration, prior acceleration. So and we get at a stage when the motion is turbulent completely, and within this stage, and for these values of the parameter, the information exchange rate is maximum. So, and it goes up from a very little value to a very high value. So here's our conclusion about this, that apparently this is very much, but completely independent. Ian and my group works completely independently, and we are arriving at similar conclusions around the same time. So this means that apparently the parameters of birds or fish are evolutionarily tuned to a value. And by parameters, I mean the tendency to align, the tendency, a very small number of parameters, are tuned such that they can easily jump into this turbulent phase. And they do this before collective decision making. the starlings do that aerial flight, aerial display before roosting, before deciding when and where to roost. And we measured simply in the simulation what is the information exchange rate, and it really is much higher in that turbulent phase. Now, I have much more material. What was 5 minutes old? Okay, I'll be fast. So we did also some experiments to support these conclusions and looked for collective motion of keratocytes, which are these were skin cells from fish. And in Hungary, we are like Canada. We didn't have to ask much for this, and we had to scratch the surface of the fish, and then the cells are released on the surface, and there's a light video microscopy. Pictures are taken, and this is a model we developed. These are sticky self-prepared particles because these are sticky. And we see that for low density it's like gas, for higher critical density it's like clusters, flocks, and for even higher density it's just a uniform motion for the keratocytes. And then you can put the keratocytes into various confined situations. Okay, so in this is 1 by 1 millimeter, and this is the corresponding simulation of a model which is a bit more complicated than before, but this back the main features of these sticky skin cells which move relatively fast. Okay, so this is illustration. Just look at it as a picture. We can also make the models more detailed. It doesn't mean that things change a lot. If we wanted to simulate people here with a herding effect, and we wanted to simulate this situation. You had a large room, 5 doors, and everyone is trying to escape. This is a panic simulation, and the pressure is shown with a color-coded, and the particles move back and forth if they feel that they are not patient. So if they cannot move ahead, they switch doors, and it's amazing that there's this extremely simple rule makes the whole system very self-organized, and they leave the arena in about the same time. But this is I show this because of it's an example for jamming. So we have seen that our systems are made of units which interact through intellectual, learned, programmed, physical, chemical, extremely simple interactions. And even though it's a line, right? This is in a way the central transparency slide, but not the last. So I would propose that these are the major observed motion classes. Disordered, of course, fully ordered, rotational, then this turbulent, quasi-long range. I told less about this, maybe ripple and other things, and jamming. And so there we have states, and we have transitions between the states, just like in equilibrium statistical mechanics, and these transitions can be very much like that. Okay, I would really like to show you some of our most recent ongoing curves, just like Ian did. I will skip the network aspects, although that's also, okay, let me show you. Within a simulation, you can, it's a bit, it's not so easy to identify the separate flocks so that they were really denser regions, and then they move back and forth. This is a half open, half closed boundary, because if they push one side of it, it can glide. So it's a very special boundary condition we put out for, okay, you see the point. And now this is the end, which will be, I think, a few minutes. We are doing what exactly what Liam said, that this is the ultimate goal of today. It's following individual units and determine the interaction between them in a flock. And we will do it for sophisticated robots, but started as a question of principle in extremely simple units. These are radio controlled, both $10 a piece, you know. And this is a sophisticated experiment. I will show you. So this is the lab with the boats, you know, and we have to develop the same visual identification of the boats. The extra point here, which I cannot show you right now because they are not there, but very soon, is that we can also control through radio some leaderboards, and we will study the question of leaders in this simple system, and then go up to more complex systems. So if you switch on, if you using a single radio wave band, you switch on them, and they start to move. What you see is what the Kudroli described, showed us for a much simpler system. Apparently, this jamming at the wall is showed up in our system also. Maybe it's hydrodynamic, maybe it's deeper, but they want to go and leave the arena and just get stuck. Then, if we order them to move backwards, our boats are such that if they move back, they rotate, they change direction like bacteria. And so then they form some other shapes. And then this is some explanation of the order parameters which are shown here, but it's enough if I just visualize for you that. So we got rid of the boats getting stuck at the border by directing them back and forth. You know. Of course, they are not stuck at the border now, but they don't order. But then you change a little bit, only a little bit, half a second of the difference between moving back and forth, and relatively quickly, this is 8 times speeded up, they find this rotational motion. So they order. Now this is the simplest experimental system which shows this, and the pigeons, I want to show you pigeons because if you are interested, because that's a very unique. This is a simulation which shows the same amazing thing, and then we succeeded in putting a GPS device on it. How much? How much I'm doing? Okay, 1 minute. So you put. Okay. So this is the real flock, and the GPS devices are quite small, 16 grams, and this is what you see here. You know, this is a computer simulation. No, sorry. This is real data visualized. So we have now data about the group dynamics of the flock of pigeons. So they go back, to feed, and these blue blinks are they just show through the backpacks the GPS. Okay, you see the rich dynamics, and this is a sort of a fancy visualization because they look like birds, but they are computer graphics. But the data, the coordinates are from our experiments. And so you can analyze all of this, I don't have time to show the analysis. This is really the last one. You can look also for leadership. So you can see that within a flock, the position of pigeon 2 is mostly before others, but there's a very complex hierarchy between the pigeons, which you can map from the data if you have a homing flight. And there are a lot of collaborators. And thank you for your attention.
Okay, can Vishwashar come and set up his laptop while we take questions? Questions? Yeah, please.
So the SPP model doesn't conserve momentum, correct? And so I'm curious about situations where you don't have a substrate, you're a low Reynolds number, when you don't have anything to push off of. What do you do? What do you think about in that case for active particles?
No, you can keep it in mind.
So if the Reynolds number is low, the bacteria can move and they can do the same thing, and the total momentum can increase. They push somehow back the fluid. Yes.
So there's no situation that you're worried about where this non-conservation of momentum should be possible?
This is the sort of sample per particles or driven systems or collectively moving systems is the science of non-conserved momentum. So we don't. If the momentum is conserved, I think no order emerges. Right? We can discuss that.
Jacques.
Yeah, I mean, I would just like to make a comment. I mean, what you're saying about non-conservation of momentum is true in 2 dimensions. The particles interact with the substrate. But then total momentum is conserved, but taking account of the substrate.
Oh, yes.
Since you don't care about that, then
Yes,
for the population.
of course.
But now in 3 dimensions, so if you worry about starlings, for instance, then momentum is conserved, but you have to keep track of the air motion. And now you have to get to
in that sense, momentum is conserved in 2D also. I mean, of course, the bacteria give their momentum to the substrate, and in 3D, the birds produce a vertex, and this vertex moves away, and it has a momentum.
Right, but then you have to keep track of the fluid motion as well. So now you need a 2-fluid description, and there the total momentum is conserved.
In the case of the keratocyte,